Hi, this is Arvid from Econ Explains, and today we are going to be talking about whether energy efficiency investments deliver. And the short answer is they can, but they don't have to. And sometimes model predictions can go very wrong. Energy efficiency investments are often presented as a win-win opportunity. And the first one is for you as an individual. If you, for example, insulate your house, you pay something to insulate it, but then you have reduced energy expenditures. Basically because it's more efficient, you need less energy, you pay less, and then so you save money and you get your investment back. So that's the first win. The second win is because you're using less energy, it's good for climate, because less emissions means less climate change. And there's been a variety of studies saying that there's a lot of these win-win energy efficiency investments out there. For example, a famous one is a 2009 study by McKinsey. And in this graph, they showed a whole range of investments, and all the bars that are negative basically are investments where you basically get more than you put in. So if an investment is $100, you get something that's like $120 out of it. So you basically gain money by doing the investment. In addition, energy efficiency is really important in a lot of climate change goals. For example, the International Energy Agency has different scenarios to combat climate change. And in some of those, when you limit global warming to 2 degrees and you keep a good economic growth. In those scenarios, energy efficiency is supposed to contribute a 50% reduction in greenhouse gas emissions. But there's a problem. And the problem is that we don't see as much of these investments as you would expect, given what we've seen from these reports. Now, there's been a lot of explanations put forward to why this is. For example, imperfect information. People don't know about it. Imperfect capital markets. Basically, it's hard for you to get the funding to do the investment. Or, for example, people don't put enough value on the future. And a lot of other behavioral biases have been put forward as an explanation. So with all these explanations in place, 3 top energy economists basically went out and analyzed this question in one of the first real big field experiments. And they did it in the United States, in Michigan, where they analyzed 30,000 households as part of a Weatherization Assistance Program. And this program basically helps low-income households implement weatherization, basically to better protect their house against the winter and to reduce their energy consumption. And the 3 authors of the paper are Meredith Foley, Michael Greenstone, and Catherine Wolford. And so they published their findings in one of the top 3 economic journals, the Quarterly Journal of Economics. And what these 3 economists found is that basically it might all be good to have these great projected benefits, but sometimes the actual savings are way less than is predicted. So the rest of the video will be as follows. First, I will discuss the main results of the paper and then discuss potential factors that can or cannot explain these results. Second, I will then move on to show 2 additional analyses that the authors did to provide a policy perspective to the results. And these 2 analyses are a rates of return comparison and analyzing what does it actually cost to reduce our climate emissions. And these are 2 tools and ways of showing data that I think we should all have in our toolbox when discussing energy and environmental policy. So now onto the main results of the paper. And first I will discuss the audit tool that is used in the Weatherization Assistance Program. And this tool is called the National Energy Audit Tool. And this tool is a widely used and freely available tool that is quite easy to use, but uses advanced computer programs. And what it does is it combines information on the house, the weather, and energy prices, and then basically determines the most cost-effective investments for the particular house. So in the setting of our paper, in Michigan, the most frequent investments were furnace replacement, infiltration reduction, and wall and attic insulation. With that being said, let's move on to the numbers. The average cost of the investments is about $4,500, and the average predicted present discounted value of benefits, according to the NEAT model, is about $9,800. So a great result on paper. And remember, the positive ratio of benefits to costs is mandatory for the subsidies to be granted. But what about the actual energy savings? Well, the author's preferred estimate of the benefits, based on their causal estimate from the field experiment, is $2,349. So the actual benefits are estimated to be only 50% of the costs. And the actual benefits are much, much lower than the predicted benefits. So what does that mean? It means that you're actually losing money on this investment instead of gaining it. Now, the authors also look at a variety of reasons why this could be the case. They look at weather, they look at the contractor quality, they look at the costs, but none of these seem to be explaining why the benefits are so low. In addition, they look at the rebound effect. What is the rebound effect? Well, the rebound effect is once you have basically a more energy efficient house, so you can get the same temperature for less expenses. Maybe you'll turn up the heat, make it warmer. But the authors found no evidence of this in the paper. And as a result, the only thing they're left with is the fact that these engineering models just overstate the benefits of these investments. So what can explain why this engineering model goes so wrong in its prediction? While they can't fully explain it, one thing they point out is that in the baseline, before any investment happens, the estimated baseline consumption of households is 25% higher than it actually is. So if you're starting from a baseline that's too high and then you say you reduce energy by 40%, naturally you're going to overestimate the benefits. So the authors conclude that there's actually not much of an energy efficiency gap at all to explain. It's simply that the costs are higher than the benefits. So when you hear of reports or predictions that are heavily based on these energy efficiency measures, especially if they're like win-win, then it's good to exercise some caution and say, well, maybe these benefits aren't as big as they are predicted to be. So while the estimate that we've seen is the author's preferred estimate, they also show a variety of alternatives. For example, they look at different lifetimes, 10 years, 16 years, and 20 years. Now, this 16 years is the author's preferred estimate because it's the average lifetime of an investment. Basically, if you do an investment, how long does it last? How long does it give you these reduced energy savings? They also look at different discount rates, 3%, 6%, and 10%. And so while we can see a range of estimates, none of these benefits get to the $5,000, which is about the average cost of the investment. So no matter what the lifetime is or the discount rate, you just don't recover your costs of investment. And a different way to then show the results is to look at, well, what's your internal rate of return? Basically, what's your return on investment? And to start with, let's take the rate of return on the stocks and 10-year treasury bonds. And the stocks, this gives you an average rate of return of about 6%. And then the 10-year treasury bonds is about 1.6%. Now, we've already seen with the predicted benefits, you have a positive rate of return. With the actual things, you get a negative rate of return. So when we're looking at the ex-ante private benefits, we see about a 12% rate of return. However, the actual private rate of return is negative at 2.3%. But the next question is, what if we add the value of the reduction in emissions? Then you jump from a 12% benefit in prediction to 50.5. And similarly, the actual private benefit goes up to 0.1. So now this is accounting for the fact that you're reducing your footprint. You're basically reducing emissions, and then those are then monetized. But there's a third category that the authors look at, and that is, what are the total benefit and cost from a social point of view? Because there's another aspect to this problem, and that is that utilities for natural gas and electricity often have a fixed cost to providing the energy. And regulations, cost plus regulation, allows them to recover this cost. But how does that work? Well, part of the price that you're paying is for their marginal cost of producing, and part of it is for their fixed costs that they have to pay no matter what. And so if you reduce your energy consumption as an individual, that means that they'll have to now go to the other consumers and charge them a little bit more to recover their costs. So a part of your reduction is basically an increase in the price to others. And their last category is then going to include basically this cost to others of you reducing your energy consumption. And using those numbers, they get to about 3.1% rate of return predicted, but actually minus 7.8% using the actual energy savings. So not a great investment, and we might want to think about other alternatives. Now, the authors present another way to look at these results, and one that I think is very fascinating. What they do is they look at what is the cost of reducing greenhouse gas emissions using these subsidies. And to interpret those results, you need an anchoring point. And the anchoring point you're going to use is the social cost of carbon. Now, what is the social cost of carbon? The social cost of carbon is, for any emission you do, say greenhouse gas, what is the damage you're causing to others? And around the time of the paper in 2012, the United States government used an estimate of $38 per ton of CO2. Now, to put that into something more tangible, if we're thinking about driving a car, if we're using a gallon of fuel, that's about 45 cents per gallon that you're causing in damages to others. Or if putting it in euro per liter, it's about 11 cents per liter. So the first thing we're going to see on the graph is the social cost of carbon, which is our anchoring point. Now, how much does it cost to reduce greenhouse gas emissions? Well, if we use the ex-ante projection and a 3% discount rate, the predicted cost of reducing a ton of CO2 would be about $38. So exactly the same as the social cost of carbon. So this policy would basically reduce something at the cost that it's actually harming others. But if we use the ex-ante projection with a 7% discount rate, then we find that it's about $71 to reduce a ton. But then if we look at what it actually costs to reduce emissions, because the actual energy savings are way less than the predicted energy savings, we then find that it's about $201 for a ton of CO2 if you use a 3% discount rate. And that number goes even further up to nearly $300 if you use a discount rate of 7%. So not only is this policy very costly in terms of reducing energy, it's also very costly in terms of reducing greenhouse gas emissions. So we might be better off thinking about alternative ways to reduce emissions. For example, a carbon tax or cap and trade, or even energy efficiency investments that have been proven empirically to have good returns on their investment. And one of the cool things is, once this paper came out and basically said, look, predicted benefits are all good and well, but what we really need is ex post evaluation using good econometrics or statistics, is that the Obama administration, when they put forward their Clean Power Plan, actually implemented some of these results in their language. Basically, in their Clean Power Plan, they drafted the fact that states have to evaluate energy efficiency investments using ex post analysis, not just with these predicted benefits. In addition, they recommended field experiments and quasi-experimental evaluations, basically state-of-the-art econometrics. And I think this takeaway also applies wider. Basically, we should stress that there's an ex post evaluation, not just on the predicted benefits, but the actual benefits, and using good econometrics. So a simple tweak that can lead a lot of benefits to make sure that we're tackling climate change in the most efficient way.